and usually big dipole. They don't really compare to bonds. And so all these IMFs are fairly weak compared to bonds, actual bonds. And so here's an ionic lattice here. You can see a lattice of ions. So it looks like high melting points, right, etc. Here's molecular, you know. If I melt sulfur, it's not as hard to melt, you know. Here's some molten sulfur. It's a lot easier to melt because what holds sulfur molecules together? Does sulfur consist of ions? No, it just consists of sulfur atoms bonded into a ring like that. There's no positive. Is one of the sulfurs positive and the other sulfur negative? No, it's not ions. And so what holds nonpolar species like this together are what? Okay, the only thing that holds nonpolar species together are abundant dispersion forces or instantaneous induced dipole. Dipole holds polar molecules together. H-bonds hold very polar molecules together. And so the only thing that holds nonpolar molecules together are these London forces. So what's holding this? Sulfur has a very low melting point. Sulfur melts like at less than 100 degrees C. So sulfur is easy to melt. Ice is easy to melt. Quartz, amethyst, citrin, are these easy to melt? These are hard to melt. Have you ever tried to melt quartz? You're going to be unsuccessful. It's extremely high melting point. Why? Because they're covalent bonds holding everything together. Have you ever tried to dissolve quartz in water? Does quartz dissolve in water? No, you aren't going to break those covalent bonds. The water molecules aren't really going to be attracted to neutral atoms, you know, in diamond, or, you know, partially charged atoms in quartz. However, even though ionic solids are strongly bonded, water can tear apart this lattice, you know, their collisions, and the water can encapsulate it. When water encapsulates the ions, we call it an ion dipole attraction, which can be quite strong. Aluminum metal, you know, metallic bonds can be strong to weak. Aluminum has a not terribly high melting point, but pretty good at melting. It's hard to melt. And so here's a little summary. Ionic, high melting, generally water soluble, brittle. Oh, this is conduct electricity. Do they conduct electricity? No, only when molten or dissolved in water. But in the solid state, they don't conduct because there's no translational motion. Molecular, these are low melting. You know, they're low melting because they're weak forces holding them together. Molecular, it depends if they're nonpolar or polar. Nonpolar molecular solids dissolve in nonpolar liquids. So CO2 dissolves like in oil better than in water because CO2 is nonpolar. However, HCl dissolves in water better than oil because oil is nonpolar, HCl is polar. And so we have a rule for this, it's called like dissolves like. And so this is nonpolar, it's a hydrocarbon that can dissolve in nonpolar liquids. Iodine's nonpolar, that can dissolve in nonpolar. So these are much better to dissolve in nonpolar than in polar. But we could have other molecular solids, like solid HCl or solid water, ice, that would be better off in polar. Then we have network covalent. These are just covalent, you know, network covalent or covalent. High melting point, this quartz, this diamond. High melting, insoluble, and all common brittle. And they don't conduct electricity except for graphite. Then we have metallic, a wide range of melting points, insoluble. These are also malleable, ductile, good electrical conductors. So those are some properties of the solids here. The properties of the solid. Okay, those are solids. Now let's take a look at the intermolecular forces in more detail. The intermolecular forces are the forces that hold the molecules or whatnot together. And when we look at intermolecular forces, we have different ones that we look at. They're starting off with dipole. This should be blue here. I started off with induced dipole because induced dipole is the weakest, and then dipole, and then the strongest would be hydrogen bonds. And so the induced dipole force is a temporary dipole. A dipole force is a permanent dipole, and a hydrogen bond is an extremely strong dipole. The hydrogen bond is the strongest of the intermolecular forces. And so here's the dipole. The dipole is like this. This has a permanent dipole, BrCl. Chlorine's more electronegative, so chlorine's going to get the negative end, bromine's get the positive end. That's a permanent dipole. And so the negative end of this is going to be attracted to the positive end of that. And so this is what we call a dipole-dipole attraction, this orange. It's electrical attraction. This orange is dipole attraction. This bromine is attracted to chlorine, the chlorine is attracted to bromine. And so we set up a whole network of dipole-dipole attractions here. It's dipole. This is the instantaneous dipole. Normally, we have two atoms or molecules that are nonpolar. But in one instant of time, let's say more electrons end up here than here. In one instant of time, there's this little wave, electron cloud. And what that does is it causes a wave here. And in that one moment in time, they're attracted. And then the wave disappears and it's gone. And so what this shows is that even nonpolar molecules can be electrically attracted in one instant. Things aren't static. So that's induced. This is showing the unusually big dipole attractions. You know, when we have fluorine, oxygen, and nitrogen, these set up big dipoles. Like, for example, ammonia would have hydrogen bonding, methylamine would have hydrogen bonding, water has hydrogen bonding, methanol has hydrogen bonding, hydrogen chloride has hydrogen bonding. Anything like this, DNA has hydrogen bonding. Anything where hydrogen is bonded to one of those, we're going to have an unusually big dipole. This is just showing, you know, the boiling point. Boiling points tell us, you know, which one has stronger forces. The higher the boiling point, the stronger the force is. So here we have nonpolar nitrogen versus polar carbon monoxide. Polar carbon monoxide has a higher boiling point, telling us it's stronger. So this is dipole. This only has dispersion. Actually, carbon monoxide has both dispersion and dipole because dispersion happens between everything. It's just nitrogen only has dispersion. Carbon monoxide has both dispersion and dipole. Higher boiling point, minus 196 versus minus 192. Let's compare SiH4 versus pH3. SiH4 is nonpolar, pH3 is polar. Polar one has a higher boiling point. Nonpolar versus polar. Polar one has a higher boiling point, but it's 77 versus 78. It's not. Oops, minus 80 versus minus 63. Sorry, it's more significant there. Nonpolar versus polar. Polar has, yeah, so the dipole is more significant. They're comparing molecules of equal size. This is why they're showing the molecular mass. They're showing the molecular mass because they want to compare things fairly. If you have a gigantic molecule compared to a small molecule, it's an unfair comparison. We got to compare things of equal size. And so that's why they show the molar mass there. What they're showing is the molar mass has an impact. The molar mass has an impact. If we look at the boiling point, methane, CH4 versus silane, SiH4 versus germane, GH4 versus stannane, SnH4. The tin tetrahydride has the highest boiling point versus methane, carbon tetrahydride. And the reason is this, is it because it's heavier? No. The reason why the tin has a higher boiling point is because it has more electrons. The more electrons it has, the more what we call polarizable the electron cloud is. And so let's say if you have, it's like the swimming pool. If you have a very tiny swimming pool, what's the biggest wave you can make? If you have a very tiny swimming pool, the biggest wave is going to be kind of small. But what if you have a gigantic swimming pool? If you have a gigantic swimming pool, the biggest wave you can make is huge because the volume of water is huge. You know, I was looking at those artificial surfing waves or something, and you know what they're building those in are not pools; they're building them in lakes and reservoirs because the volume of water. And so the same thing here. The reason why this has a much higher boiling point is because it's got a lot more electrons, so it can build a bigger wave, basically, and have stronger dispersion. So all these are dispersion. Now, these are showing hydrogen bonding. Hydrogen bonding interactions are very, very strong. These are all polar here. But if we follow the trend here, you know, more electrons, the bigger the wave, the bigger the dispersion. So all these are going up like this because the more electrons, the bigger the wave. More electrons, the bigger the wave, right? Except what falls out of place? What falls out of place is ammonia and water. Why do these fall out of place? These fall out of place because of unusually strong dipoles, which are called hydrogen bonding. Now, what we're doing here is, yes, the bigger the wave, the stronger the dispersion. And so the bigger the pool, the stronger. The more electrons, the stronger. So the same thing, more electrons, the stronger. Well, what's going on here is it's more polar. And so more polar, more polar. And so there are two factors going on there. But, you know, you don't have to memorize this chart. I'm just showing. All right, so there's some properties of solids. Now, next what we're going to talk about are some properties of liquids. Solids, can they be compressed? Solids can't be compressed. I mean, they're already bonded to each other, they're touching. Gases can be compressed, liquids cannot. Liquids cannot be compressed because the particles are still touching each other. So you can't really compress liquids. You know, gases can expand, liquids cannot expand, solids cannot expand. Gases have low density, liquids have high density, solids have high densities. Gases may be mixed in a fixed volume, liquids cannot. Liquids, you'll have to add to the volume, solids as well. Gases exert constant pressure, liquids don't. Liquids have higher pressure and solids have higher pressure on the bottom than at the top. And so those are just some basic properties. Now, we're going to look at some other properties of liquids. So let me just list all the properties here on the board. Actually, we'll just go through the slides here. One property is vapor pressure. You know, how easy is it to vaporize a liquid? Some liquids vaporize easily, others vaporize with difficulty. And what happens in vaporization is this. Some molecules have enough kinetic energy to escape the surface. Here. This is vaporization. So these up arrows are vaporization. What can happen though is the reverse process. Do you know what the reverse process is? The water comes crashing on the surface and sticks. It's called condensation. So we have vaporization and condensation processes occur. And so some liquids readily vaporize, others don't, like alcohols. Do alcohols vaporize easier than water or more difficult than water? Easier, so those are more volatile, we say. They're held together by weaker. The stronger the intermolecular force is, the less vaporization there is. Maple syrup, does maple syrup vaporize easily or more difficult than water? More difficult. And therefore, the forces, intermolecular forces, are stronger in maple syrup than they are in water. The forces in maple syrup are hydrogen bonding and dispersion. We have something called heat of vaporization. Heat of vaporization is the amount of energy it takes to vaporize. That's called delta H of vaporization, heat of vaporization, endothermic. And So here, if we want to vaporize the water more rapidly, boil it. Well, boiling costs us energy. How much energy? Well, it's delta H of vaporization. Now, if we have steam, the steam, when it condenses back to liquid, is exothermic. It releases energy. So steam burns are considered very, very severe because of this. When steam condenses back to liquid water, a tremendous amount of energy is released. When liquid water is vaporized or boiled, a tremendous amount of energy is absorbed. So when you try to boil your water, you have to start this early because it takes a lot of energy to boil it. What is that energy? It's this energy. That's the heat of vaporization, delta H of vaporization. Now vapor pressure, should talk about this. Vapor pressure is this. We measure this, we cap this off, and then we just let this naturally vaporize. We could heat it, and if we heat it, it's going to generate more vapor, right? But normally, even at room temperature, it generates vapor. When the air here is saturated with water vapor, we call it 100% relative humidity. That's the vapor pressure. We can measure that. We can measure the pressure of the water molecule that it exerts when we hit 100% relative humidity. This is what it looks like. So as the water gets hotter and hotter, the vapor pressure increases. That's exerted by the water molecule. So as the water gets hotter and hotter, we get more vaporization, which fills or saturates the air with more water vapor. Eventually what happens is we fill that container with so much water vapor that the vapor pressure of the water hits 1 atmosphere. When the vapor pressure of the water hits 1 atmosphere, it begins to boil. And that's what we call the normal boiling point of water. And so below 100 degrees C, the vapor pressure is lower than atmospheric pressure, but when we hit this, then it's going to boil. Ethanol is more volatile. It doesn't require as much temperature to vaporize. Dialkyl ether is even more volatile than ethanol. That's easy to vaporize because in dialkyl ether, we only have dipole. In ethanol, we do have hydrogen bonding, but not as much as in water. In water, we have more hydrogen bonding. So we got H bonds. We got H bonds here, but weaker H bonds here. We only have dipole. Methane is way down here. Methane is extremely weak because there's only instantaneous dipole or dispersion forces. So that's what that. This is the vapor pressure equilibrium. Here, this is what we call less than 100% humidity. It hasn't been saturated, so this is dry air. And then it's starting to humidify. And so this up arrow is showing the vaporization, we get more molecules. And it's showing the condensation. A few molecules strike the surface and stick. As more molecules get put in the vapor state, then the condensation rate increases because there's just more molecules coming in and hitting. I'm going to stop in just a minute here. Eventually, we're going to hit this point where the vaporization rate is equal to the condensation rate. When the vaporization rate and the condensation rate are equal, we've hit 100% humidity and no more dissolved. So this is dry air becoming more and more humid, and eventually it's going to hit 100% humidity. Once we hit 100% humidity, it doesn't change. Okay, I'm going to stop here and then we'll